All right, so here's a lesson video about what we're about to learn. I hope it plays. It looks very freezy. What? Can't I skip this?
Look at what a sequence does as n approaches infinity. If the sequence asymptotically approaches some finite number, it is convergent.
This is from last
time.
time.
If it does not do that, it is divergent. Now that we understand convergence and divergence for sequences, let's apply this understanding to series. First, we have to recall what a series is. When we try to add up all the terms in an infinite sequence, we get an infinite series. This can be represented by listing out all the terms, but it can also be abbreviated using the summation notation we already learned with the uppercase sigma. We can talk about convergent and divergent series just like we did for sequences. Starting again with a simple example, simply n, we can easily see that if we were to add up all the positive integers, which themselves go to infinity, certainly their sum will also be infinite. This can be demonstrated by forming a new sequence where the first term is the first term of the series, and then the sum of the first two terms of the series, and then the first three terms, and four terms, and so forth. The limit of this sequence is the sum of the original series, and the sequence will go to infinity, so the original series is clearly divergent. Can any infinite series be convergent? That is, can an infinite number of terms add up to give a finite number? Well, when we looked at improper integrals, we saw exactly this sort of thing happening with a limit of integration going to infinity, but still yielding a finite value for the area under the curve. So we shouldn't be too surprised that convergent infinite series exist. Take, for example, 1 over 2 to the n. Listing the first few terms, we get 1/2, 1/4, 1/8, and so on, approaching 0. Let's use the same technique as before, creating a new sequence and listing the first term of the series. Then the sum of the first two, which is 3/4. Then the sum of the first three, which is 7/8. And if we continue on in this manner, we see that this sequence approaches 1. Therefore, the sum of this series is equal to 1, and we can say that it is convergent. Different types of series will have different requirements for convergence. Take this generalized geometric series. If we recall the definition of a geometric sequence, it is one in which you multiply each term by some constant to get the next one. So starting with A, we get AR, then ARR, or AR squared, then AR cubed, and so forth. So a geometric series is just the sum of these terms, or the sum of A times R to the n minus 1. We will find that if the absolute value of R is greater than 1, a geometric series will be divergent because these terms will get bigger and bigger and therefore go to infinity. If equal to 1, we are just adding up infinitely many A terms, which will also be divergent. But going back to the sequence, if the absolute value of R is less than 1, as it is raised to bigger and bigger exponents, each term will get smaller, and the limit of the sequence will be 0. So the series, or the sum of the terms, will be convergent, and the sum will be equal to A over the quantity 1 minus R. In fact, an important theorem states that in order for a series to be convergent, the sequence that generates the terms in the series must have a limit of 0. This makes sense because if the limit were any other number, or if the sequence itself was divergent, there would be no way for the terms in the series to add up to a finite value. And even if the limit of the sequence is 0, it is still not a guarantee that the related series will converge. So sometimes we can look at a series and state that it is divergent simply by showing that the sequence it is derived from does not converge to 0. Take something like n squared over the quantity 5n squared plus 4 from 1 to infinity. To assess the series, let's just look at the sequence of numbers we get from this expression without considering their sum. What is the limit of this sequence as n approaches infinity? Well, we need some algebraic manipulation first. Let's divide both top and bottom by n squared so that we aren't plugging in so many infinities. On top, we get 1, and on the bottom, we get 5 plus 4 over n squared. Now we plug in infinity, and this term goes to 0, leaving us with 1/5. The sequence does not converge to 0, so the sum of this series that includes all the terms from that sequence must be divergent. Now that we understand the concepts of convergence and divergence as they apply to both sequences and series, we are ready to move forward and learn more about series.
Okay, so now you guys know everything there is to know. There's no more I can teach you. But I will teach you this lesson again right now. Okay, so did I do this right? Did I share my Elmo? You guys see my Elmo? Word.
Yeah.
Thanks. Okay, so like what he just did in that 4 minutes is our lesson today. Everything he talked about is our lesson. What does it mean for a series to converge or diverge? How do we use the geometric series test? And then how do we use the nth term test for divergence? Those are the 3 things we talked about. That's what we're going to talk about here in the lesson. In algebra 2, so even in honors pre-cal, you guys didn't get into infinite series apparently. In honors algebra 2 and regular algebra 2, I don't know if you had regular algebra 2, right? You do a whole unit, at least in honors algebra 2, is towards the end of sequences and series. And there's 2 types of series. There's arithmetic and there's geometric. And you guys learned all these formulas that go along with it. When we did that, though, we never added up infinitely many numbers. Like the number on top of sigma was always a number, like 10 or 15 or something. Well, now what we're doing, that top number is always going to be infinity. We're always going to be adding an infinitely many number of terms. And the whole discussion, the whole chapter is about, okay, if we have an expression inside of sigma and we add infinitely many of those terms, does it converge to an actual value or does it not? That's the entire chapter. Our entire chapter is we take these tests and we look at the problem and we're like, oh, on this one, we're going to use the ratio test. And then we apply it. And then on the next one, it's like, oh, on this one, we're going to have to use the integral test. And then we apply it. You pretty much never get to choose which test, you don't get to fall in love with the test and then use it every single time. Like the way the problem looks will dictate which test you need to use. Okay. It's not the most glamorous or fun stuff, but I have learned by the end, it's not as bad as what I initially thought when I first started teaching this chapter. It's not bad, even though it looks like a lot. So I have these notes here, and let's talk about just in general what it means to converge or diverge. So in the lesson video last time, you guys dealt with sequences, a sequence of numbers, just a list of numbers. Well, a series is when you take those terms of the sequence and you add them all together. And that's what we're doing today. On the notes, some of the stuff didn't transfer, but like in between these plus signs, there should be like ... like ellipses, which I know doesn't seem like should be a big deal, but you guys are eventually going to be writing stuff like this. And where those dots need to go, you actually need to put them or you don't get your credit, to signify that there is other stuff there. So there's a lot of places on these notes where the notation didn't transfer over. Like, especially on this one here, where we're adding up infinitely many numbers, there should be plus dot, dot, dot on the end of the a sub n, because we're never not adding numbers together. So I want to kind of explain this box, but I want to do it through example 1. Example 1 is what he had in the video. It says, find the sequence of partial sums. What that means is, the sequence is 1/2, 1/4, 1/8, 1/16. But if we talk about the sequence of partial sums, well, that looks a little bit different. If I want to do the first sequence of partial sums, like S sub 1, all that means is that's whatever the first term is. So in this case, S sub 1 is 1/2, the first term. S sub 2, however, is not 1/4. S sub 2 is whatever you get when you add 1/2 and 1/4 together. You're basically creating a new sequence. The first term, then the sum of the first two, then the sum of the first three, and you're creating a new sequence of numbers. And that's called the sequence of partial sums. So 1/2 plus 1/4, that's going to be 3/4. We actually want to get what these values are, because we're going to have to turn this into an expression. We're going to have to write a formula for this new sequence. The sum of the first three is going to be 1/2 plus 1/4 plus 1/8. Which you add all those, you get 7/8. So imagine I now have this new sequence where it goes 1/2, 3/4, 7/8, and it's going to go on forever. Okay, that's what's happening. That's called our sequence of partial sums. If that sequence is approaching a number, like as I go out to infinitely many terms, if that sequence is approaching a number as n goes to infinity, then we say this series converges. Like if that limit exists, then that series converges. If that sequence that I just generated, if it's not approaching anything, then we say that series diverges. So the way we're going to analyze that is this. We're going to create a formula for this. We're going to create a formula for S sub n. This, I can remember doing this stuff back in Calc 2, just seeing sigma all over the place. I was so bad at this stuff. I don't know if that puts any confidence into you guys whatsoever, but I did fine in the class, but I felt like I never knew what I was doing. Like, I remember just winging it, trying to create these formulas. I was not good at it. But basically, I need to create a formula for the terms here. Well, I look at the bottom, and I look at, okay, if n is 1, then the bottom number is 2. If n is 2, the bottom number is 4. If n is 3, the bottom number is 8. So what's happening in the denominator of this sequence? How do I write an expression for that? 2 to the n. 2 to the n. Very good. And I can see that because, okay, if I do 2 to the first, I get 2. If I do 2 to the second, I get 4. If I do 2 to the third, I get 8, and so on. So that's how I can kind of look at these and see that's 2 to the n. The top number, okay, now I got to find a relationship between 1, 3, 7. Well, this one I can kind of see that top number is always 1 less than the bottom number. So it's going to be whatever the bottom number is minus 1. So this is our formula for the sequence of partial sums. Now, in terms of converging or diverging, if this sequence, as n goes to infinity, approaches a number, then this series converges. So now I'm going to look at the limit of this expression as n goes to infinity. Meaning this sequence that I created right here, are those numbers approaching a certain number? You can kind of see what it's approaching. I mean, eventually you're going to get to a big number on bottom and just 1 less than that on top. So you can kind of see intuitively it's approaching 1, but let's do some analyzation here. So if you look at this and you can't tell it's 1, we can do some algebra. I can take each term in the numerator and divide it by 2 to the n. So I can rewrite this as Well, 2 to the n over 2 to the n is just 1. And then minus 1 over 2 to the n. I'm just dividing each term on top by 2 to the n. And now I can do my limit stuff. I can see, if I would plug in air quotes infinity, this bottom number is going to be gigantic. 1 over gigantic is 0. 1 minus 0 is 1. So since that limit exists, then I would say this infinite series converges. Now, the nice thing is, this is not a process that you're going to have to be doing a whole lot. This is where these tests are going to come into play, where you're not going to have to create a lot of these formulas. So if you're sitting there and you don't like coming up with those formulas, you're not going to have to do a lot of that. This is just getting into the understanding of what does it mean to converge in general. If I look at the next one, all right, well, I'm going to list out S sub 1. So the first term is 1. S sub 2. So now this is the sum of the first 2 terms. So 2. S sub 3 is the sum of the first 3 terms. So 3. So if I wanted to create my formula, what S sub n is, well, just n. And so now the question is, if I take the limit of this as n goes to infinity, well, I'm going to get infinity, which means this series diverges. Okay, so again, that's just what it means for a series to converge or diverge. Let's look at our first 2 tests. The first one is the geometric series test. Like I said, this is exactly what they learned in honors pre-cal. So, the last couple of years we had a bit of an advantage because when we talked about this, they all kind of remembered it because it was like one of the last lessons of the entire year. So they were like, oh yeah, I remember doing this. It's pretty easy, but it does help had you seen it before. So in general, a geometric series is where term by term, you're just multiplying by the same exact number. So for instance, forget about series and all that, just to refresh your memories. If I had 2, 6, 18, oh gosh, 54, 162, ... So if I look at this sequence, I notice it's multiplying by 3 every single time. This is a geometric sequence where it has a common ratio. Arithmetic, which we won't get into, but in algebra 2, you learn arithmetic where it goes up by the same number every time, like 2, 4, 6, 8, 10, 12, where it's going up by 2 every time. So this is about geometric series. All right. So here's what we need to know. A geometric series will diverge if the absolute value of r, so the number that you're multiplying by, if the absolute value of that is greater than or equal to 1, it will diverge. And try to understand why you're multiplying by a number bigger than 1, your terms are getting big, so it's going to diverge. Whereas if you're multiplying by a number less than 1, so like by a half, your numbers are getting smaller, 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 smaller. So that is really what we need to know. If you look at your blue sheet, that's the comment it makes. So if we have something in the form of a number times a ratio to n or n minus 1, then it's going to, you see your columns, you can see how to work this test, will converge if, and then it tells you, will diverge if, and down here. So this little chart is going to be kind of your friend as you're working through assignments, especially later in the chapter once we learn all these tests. This is going to be your friend. The nice thing about infinite geometric series is this. Most of the infinite series we do, we can determine if they converge or diverge, but we pretty much on most of them can't tell what the series will converge to, which frustrates a lot of students. Like a lot of times we'll be able to look at a series and be like, and do our test and say, yeah, that one will converge. but we don't know what it converges to. The geometric series is nice because it's the one series we actually can have a formula and we know what the series will converge to. So this is one of the more common questions they'll ask on the AP test because we can actually figure out the sum. So we'll talk about that. Okay, so if it does converge, if the ratio, the number that we're constantly multiplying by, if the absolute value of that is between 0 and 1, it's going to converge. And not only do we know it will converge, this is what the sum will be. This right here is a super important formula for you to know. This formula tells you what all the terms, if you add up all infinitely many terms, this formula tells you what the sum will be. It's very nice. Now, important to note, A in this formula is the first term. A is the first term. So you may need to plug in whatever that lower index is, like to the thing to find the first term, and that's what A will be. I didn't know that 2 years ago. It seems like such an easy thing that I should have known. I didn't know that 2 years ago, and they took a quiz. I don't know if you have a quiz next class or the class after, but every single person missed the problem on it because I didn't tell them that. I didn't know it. So they missed it. I gave them credit, but I didn't know that. So that's important for you to know. All right. So it says, determine the convergence or divergence of the series. If it converges, find the sum. Well, it's not a very hard test to use, but sometimes you have to do some manipulation to get it into the correct form. If I'm just learning this, like if I always try to put myself in your chairs, and if I'm just learning this, I might look at this and think R is 3/2. I might sit there and think R is 3/2, so this diverges. But I can manipulate this in such a way where I write it like this. Where I pull that 3 out in front, so it'd be like 3. I wouldn't write this particular line, but I will explain it. Where it's 3 and then 1/2 to the n. Well, then what we can do is take that n and just pull it out here. And I'll explain why. I can pull that n outside. The reason I can pull that n outside is because let's say I did distribute the n back in. Well, 1 to anything is always going to be 1. So we still get that 1 on top, and then we would get the n on bottom, 2 to the n. So we'd get back to where we started. But just through some manipulation, now I can see that this actually is a geometric series. I have a term being multiplied by some ratio to the nth power. It doesn't matter if it says to the n or to the n-1, like that doesn't matter. When we find the actual sum, that will matter, because we'll have to find the first term, but that doesn't matter. So I look at this and I'm like, okay, since the absolute value of R, which is 1/2, since that is less than 1, this will converge. So what I'll write is this, okay? I won't just write converge, you're gonna have to write why. So I would say the absolute value of R equals 1/2, which is less than 1. Like that's what I'm after, that's the reason, that's what I'm looking at. So the series converges by the geometric series test. On your assignment tonight, I made a note on Canvas, like when you look at the worked out solutions, they say like converges by theorem 11.1-9. You ignore all that. You guys don't need to know theorem numbers. You just have to know the names of these things. So ignore all those numbers. So not only do we know this converges, we can actually figure out the sum. We can find the sum. We can do A over 1 minus R. We can figure out if we would add all these numbers together, what will we get? So our sum is going to be, well, A is the first term. We have to find the first term. And the way we find the first term, we take whatever the lower index starts at. So in this case, 0. And I'm going to plug 0 in for n. So when I plug 0 in for n, I get 3 divided by 2 to the 0, which is 1. 3 over 1 is 3. So the first term is 3. And then it's over 1 minus whatever our ratio is. In this case, it's 1/2. So 1 minus 1/2. So 3 divided by 1/2 is 6. That's what if I add up all those infinitely many terms, you get 6. I always think it's kind of fun just to, you don't have to do this. This is just my brain. I don't know why I think this is fun, but I always like to list out like the first few terms and be like, that's interesting. Like if I plug 0 in, we'd get 3. You don't have to write this. This is just my own little kicks and giggles. If I plug 1 in, I'd get 1.5. If I plug 2 in, I would get 3/4. If I plug 3 in, we'd get 3/8. And I just like to see like the numbers. Like it's just fun to me that if we add all this till forever, it would like add up to 6. I don't know why that's fun for me. It's just interesting. Okay. Next one. So this one is already in the format. I know there's no number in front of the parentheses, but there technically is. There's a 1 in front of the parentheses. So this is in the geometric series format. It's 1 times 3/2 to the n. So that means our R value is 3/2. So since the absolute value of R is 3/2, which is greater than 1, this series diverges. With these, one thing I've learned through having taught this class for 3 years now and being able to see a lot of AP style questions, it's rare that these types of problems show up on FRQs. They do, but it's rare. It's more likely what I found they like to do is they put it as a multiple choice problem. And what they do is this, they'll put like 3 different series. They'll put like series 1, series 2, series 3. And then they'll say, which of these series converge? And then it'll say like, choice A will be like option 1. Choice B will be like 1 and 3, none of the above. And so it's a way they can have one question where they're not spending a ton of time on a full length AP test, but they can assess your knowledge of like 3 different tests in one problem. So that is pretty common that I've noticed. All right. The next thing is the last thing that Professor Dave talked about is the nth term test for divergence. Essentially, you eventually need to be adding nothing in order for a series to have a chance to converge. That makes sense? Like your final term, if you're adding infinitely many things together, you eventually need to be adding basically 0 to get to a number. Where if you're not eventually adding 0, you automatically know the series has no chance to converge, it has to diverge. So this test, this is super important. This test only tests for divergence. This will only tell you if a series diverges. It will not tell you if a series converges, which we'll talk about at the very end, the very last example, okay? So most important here is this. This bottom box is like more important than the 2 things. If you take the limit of the sequence, the thing inside of the sigma, if that sequence does not eventually turn to 0, that series diverges. So we're going to be doing a limit of that sequence that's inside of sigma. If that doesn't equal 0, it diverges. On the flip side, though, here's the thing. If that limit does equal 0, you can draw no conclusion. If eventually you are adding nothing, it doesn't mean the series converges. And another thing I learned at a conference is 19 out of 20 times they said the limit will equal 0. Probably on this type of problem, here's the thing, on a problem like this, probably one of them is going to diverge by the nth term test, by this test. Like one of them, you'll be able to know it diverges. The other two, the last term will be 0, but you still have to use other tests to determine if it diverges or converges. But typically, this is going to turn out to be 0. So let's look at an example here. So the very first one, we have the series from n equals 0 to infinity of 2 to the n. Okay, it's pretty clear, like cut and dry, that I can look at this and know there's no chance that this will converge. And that's important for you guys to get some intuition on here. Yeah, you guys are going to learn these tests and conditions, but you're going to want to rely on, towards the end of the chapter, once you learn all this stuff, you're going to want to rely on some intuition. Okay. This, I mean, imagine us writing these terms out. If I plug 0 in for n, I get 1. Then if I plug 1 in for n, I get 2. And then I plug 2 in for n, I get 4. And then 8. There's no way if I add all these numbers together that it's ever going to get to an actual value. So I know this diverges. But mathematically, using this test, here's what I would want to show. The limit of this sequence right here, as n goes to infinity, equals infinity. Which I'm no math teacher, but that does not equal 0. So this series diverges. It is important for me to point out again, and I'll point it out again, and I'll point it out again. If this value did equal 0 right here, I would not write convergence. We would then have to do more analysis. Okay, it's inconclusive. Next one. I do think it's always fun to plug in and just kind of get some terms, and I think it helps develop the intuition. Factorial, you guys do factorial. Where do you do factorial? Combinations and permutations, right? Did you guys get to those in honors pre-cal?
That was the last thing we did.
Was it? Because we do it in algebra 2, but I just don't know. Yeah. Okay. So, but you guys know what it means, right? All right. So if I plug 1 in for n, 1 factorial is 1. And then, so I get 1/3. So the first term is 1/3. If I plug 2 in for n, I get 2 times 1, so 2 over 5. If I plug 3 in for n, so factorial, in case you guys don't remember, factorial means you take that number and you multiply it all the way down to 1. So 3 factorial would be 3 times 2 times 1, so 6. So 2 times 6 plus 1 is 13. Thought they were done February 1st on the roof. Maybe they just like being up there. So that's what I got going on here. What does it look like that those numbers are approaching? You had to guess. 1/2. Yeah. And it does. In fact, I'll show you some algebra. We can verify it is 1/2. So those terms are not going to 0, which means this diverges. Like we eventually have to be adding nothing. And this is getting closer and closer to 1/2. And I can show you mathematically that it is. So I'm going to take the limit as n goes to infinity of n factorial over 2n factorial plus 1. He did something in the video. So in the video, there was an example right towards the end. Oh, what did he have? Oh, it was n squared over 5n squared plus 1. It was something like that. Now, you guys should be able to look at this and know that it's 1/5 based on horizontal asymptote rules. The powers are the same. It's 1/5. He did some analyzation, which I actually used to teach it this way, where he divided everything by n squared. Because then you have 1 over n squared here, which goes to 0. We can actually apply that process here. If I divide everything in this fraction by n factorial, so if I divide this by n factorial, divide this by n factorial, divide this by n factorial, look at what we end up with. So on top, n factorial over n factorial is 1. On bottom, that's just 2 plus 1 over n factorial. And now I can see, oh, when n goes to infinity, this 1 over infinity factorial is 0. I get 1/2. That means the series convergence. Don't let this confuse you. You know, you start doing all this stuff and you're like, oh, that means that all these add up to 1/2. No, this means you would eventually be adding 1/2 like every single time, which means it will never converge. You're always adding 1/2. So this diverges. I guess I should say 1/2 does not equal 0. That's how I draw my conclusion. And the last one. All right. So I'm just going to write out term by term. I think this is helpful when you guys do start taking your tests and quizzes over this stuff. I think if you do list out, you have to list these terms out? No, but I think if you do list them out, it does start to help develop that intuition about what is going on term by term. So if I plug 1 in for n, I get 1. If I plug 2 in, I get 1/2, 1/3, 1/4, ... Does it look like eventually we're adding 0? Yeah. And I can show that if I take the limit as n goes to infinity of 1 over n, that does equal 0. This is what is typically will happen. Typically, 19 out of 20 times they said it will equal 0, but you can't say this converges. All we know is that it might converge, it might still diverge. We can't draw any conclusions. It's indeterminate form. In fact, this is called the harmonic series. This becomes a really important series for us. Last year, I said the phrase harmonic series, and some people in music knew what I was talking about. They mentioned it. I don't know. There was a bunch of band people. And
it is the harmonic series, but it's like completely different.
You think it's completely unrelated?
No, it's not completely unrelated. It's based in the actual harmonic series of a wave. Like that's oscillating, but it's the scientific application for the context.
No. So this series is called the harmonic series. And the reason it's important is because we're eventually going to be getting into these like comparison tests where we take gross looking series, but we're able to compare it to ones that we know converge or diverge, like basic ones. And based on how they compare, we can make analysis. So this becomes a really important one that we're eventually going to know this diverges. And so we're going to use this one and compare it to other ones to determine if they converge or diverge. So even my point is, even though the limit of this goes to 0, like we're eventually adding 0, this actually does diverge. And so I want to show you guys what time we got. Oh, perfect. I actually want to show you guys because to me, if I looked at this and I'm like, if I'm eventually adding 0, how does it not converge? Like in my mind, that doesn't make sense. Like we're eventually adding nothing. How do we not get to a number? And so I'm actually going to show you guys 2 different proofs about this diverging. So the notes are done, but I just want to show you a couple different kind of cool things. I'm going to show you one YouTube video that I found, and then I'm going to show you a proof that I actually like a little bit better, a little more intuitive. So bear with me, you guys at home. What is that? My stomach is growling. I'm leaving after this block. I get to go home. Took a half day. We're leaving to go to French Lick and go skiing. Yeah. Visual proof. I was going to take the whole day off, and I was like, I can't do that to my BC Calc kids. So I came here today for you guys. Here it is. The reason I think that, so there is a proof I like better, But the reason I'm showing you this one is because he does this proof in terms of like integration almost. And we do get, one of our tests is called the integral test, where we compare these infinite series to improper integrals, which we know how to do. And so that's one of the reasons why I want to show this video, to kind of link those things together. So bear with me for like 30 seconds. Time me. No one's timing.
Everyone, it's Brian. In this video, I want to talk about.
Nope, not ready for you yet, Brian. You guys at home are harshing my buzz because your person bar is at the top, and that's right there. It is. Oh, you guys are already sharing. Oh my gosh. Okay. There we go. So this is the proof of the harmonic series diverging. Kind of interesting.
Everyone, it's Brian. In this video, I want to talk about this series. It's called the harmonic series, and it's arguably one of the most famous series ever. And it goes like this. It goes 1 plus a half plus a third plus a fourth plus a fifth on forever. And so the natural question is, does that add up to something? Maybe it adds up to infinity. Maybe it adds up to 100. I don't know. If you add up those decreasing fractions forever, what do you get? And it's not so obvious when you start thinking about it. So I'm going to provide you with an answer to that question. And I'm going to do it in a visual way, and I hope it makes sense when you see it like that. This is my favorite proof of it, and so I hope it's your favorite too. I'm going to start like this. I'm going to graph something, and I'm going to graph the function not 1 over n, but 1 over x. So if you remember from pre-calc, 1 over x looks something like this, kind of downward sloping forever and keep on going closer and closer to the x-axis. And so I really only care starting at 1, right? 1 up to infinity. So if I start here at 1, well, if I plug 1 into the function 1 over x, that would just be 1 over 1, or 1. And now what I'm going to do, starting here, is I'm going to graphically represent this series, 1, 1/2, 1/3, and so on. And I'm going to do that with blocks or rectangles. So the area of the rectangles I'm going to draw are going to represent this series. So I'm going to start right here. So if I go from 1 to 2, this rectangle I've just drawn has a width of 1 and a height of 1. So it has area 1, 1 by 1. So that represents this 1 in the series. And if I keep going here, notice if I plug 2 into the function 1 over x, that should give me a half. And then if I draw this rectangle from 2 to 3, it has width 1 and height 1/2. So this rectangle has area 1/2, and it represents this 1/2 in my series. So I could keep going like this. This next rectangle would represent the 1/3, and the next rectangle would represent the 4th. And I could do this all day long, but I guess I should stop somewhere. The thing to notice with these rectangles is they're over the function 1 over x. They're bigger than the graph is. What if I were to take an improper integral of the function 1 over x? What if I were to integrate? And I can do this because this is a function, not a series right now. So this is a improper integral from 1 to infinity of my function 1 over x dx. What happens if I do this? Well, I guess if I'm going to do this, I need to turn this into a limit. I'll say, let's let t grow to infinity. And I'll integrate from 1 to t instead. Well, the antiderivative of 1 over x isn't too hard. It's just natural log absolute value of x. And I'll evaluate that from 1 to t, with t tending toward infinity. Well, natural log of 1 is 0. I'm not even going to bother writing that. So what I've really got here is just natural log t. As t goes to infinity. Well, what happens to the natural log function as it tends toward infinity all the way to the right? Well, if you remember, it goes to infinity, right? It just gets bigger and bigger and bigger. Definite integrals, even improper ones, represent the area under the curve, which means the area under this curve I initially drew from 1 to forever, that area is infinite. There's an infinite amount of area under this curve. But hold on. I said that these blocks, the area of these blocks, was bigger than the function. The amount of area of these blocks is bigger than the area under the curve, which I just found to be infinity. So the area of the blocks is bigger than infinity. Well, if that's true, certainly this series must equal infinity, or you might say that it diverges. So this is just one of the many proofs of the harmonic series diverging. There's many others you can find online, but this is my favorite because I can actually see it. I can see that the blocks are bigger than the area under the curve. And when I integrate to get the area under the curve, it's infinity. And so the series is bigger than infinity, so it diverges. Okay, I hope you liked this video. If you did, give it a thumbs up. And if you want to see more math videos every single day by me, hit the subscribe button. Thanks for watching and have a great day.
I do not subscribe to him. I wonder if he's still around. I don't know how long that video was made. So that was a visual proof. That one's okay. I like it because, like I said, it does link the integration process and the series process, which we get into in this chapter. So I do like it for that reason. It also goes back to left Riemann sums, overestimating with a decreasing function, which that was going on there. But the one I like, which to me is more intuitive. Where's my Elmo? There it is. Share. I like this one better. This one makes even more sense, a lot quicker to me, that the harmonic series diverges. So the top series here is the harmonic series, 1 plus a half plus a third plus a fourth plus a fifth. And then I wrote a new series below it. 1 plus a half plus a fourth, an eighth, an eighth, an eighth, an eighth, a 16th. It would go on. And so the reason this is intuitive to me is this: these 1/4 add up to a half. These 1/8 add up to a half. And if I notice, this top series is bigger than this bottom series, because all I've done is taken this 1/3 and I made it less. I took this 1/5, 1/6, 1/7, and I made them all less. So this top series is bigger than this bottom series. And the bottom series, if I keep this pattern going, I basically have 1 plus a half plus a half plus a half forever. Like I'm always adding 1/2, which means this bottom series diverges. I'm never adding nothing. And if the top one is even bigger than that one, then it has to diverge as well. So I like, to me, that's a little more intuitive, but bottom line, you're going to have to know the harmonic series diverges. Like the two big ones are going to be this. You're going to have to know this one diverges. And then interestingly enough, this one converges. As soon as this power on n is above 1, then it actually converges, even though it looks like the same graph. Crazy. Okay, you guys at home are free to go. You have an assignment on Canvas. And you guys stay classy. Have a good weekend. Bye.
Have a good weekend.
Thanks. Sam, what's your favorite restaurant?
My favorite restaurant?
Yeah.
I'll think about this.
All right, give me your top 3. It should be easier.
There's a seafood place called Juicy.
Where's that? I've never heard of it. It does sound fake.
I don't know. I'm not really good with like directions, but it's
Like what city?
like, like 30 minutes away. Minneapolis, I think.
Indian. Okay. That helps.
What?
What else? What else you got?
Like Benihana, to put the food in front of you.
Yeah.
Um, hmm.
Do you like it because they cook the food in front of you, or do you like the food?
Food's all right. I don't really cook a whole lot of food. And I like quantity.
So that's not going to be your favorite.
Yeah.
Okay. What else?
I gotta think. I don't usually go out to eat a lot. I gotta think. It's like Texas Roadhouse. Number 3.
Yeah.
So I like the rolls.
Well, I think you should go to Juicy's for your birthday,
Maybe.
or at least get some carry out or something. You know, if you don't want to go to the restaurant, DoorDash it. It'd be an expensive DoorDash. I never use that.
I don't think I've ever DoorDashed anything.
My wife did like twice. And then I saw how much it costs. I was like, what are you doing? I can go pick it up. I don't mind driving. Not as much as what the DoorDash fee is, and then having to tip them. Because you're not gonna not tip. I guess. Even if I get terrible service at a restaurant, I tip
You still have to tip. I mean,
Twen-
it's part of going in.
20%. Yeah. Well, I think you should get Juicy's.
Which one you need?
It's a weird name for a seafood place. Because you don't like you think of burgers.
It's like a big. Yeah, I don't know if I'm.
Yeah.
It's like a big bag. And then they shake everything.
A marinade?
Yeah, but it's like